All right, hello and welcome, guys. My name is Nick Saldana. This is part 2 of my STEAM project video. This one we're going to be talking about slope of the tangent line. So let's get right into it. Go here. Sure. Awesome. So, talking about slope of the tangent line, the tangent is, I'm sure everyone knows by now, but let's just go through it. The tangent is the point on a line where it touches it is a line that touches a point on a graph. Oh, that's rough. Just once. And basically it gives the instantaneous rate of change at that point. And finding the slope of the tangent will do that for you. So let's read this little blurb. Before taking calculus, when asked to find the rate of change of an equation, we often took two values on the slope of the function, applied this ugly formula right here, y2 subtract y1 over x2 subtract x1. This method is essentially taking the average rate of change over the given interval which the secant line connects. While this method is viable on a basic level, it's not very accurate and has an alternative. What I mean by this is, as we remember from grades 9 to 11, when asked to find, let's say we want the rate of change at that point, we would do a couple of things. So let me switch colors to black. We would either just have it in the middle and take, oh gosh, that is not straight at all, but we have that sort of thing where we're calculating the slope closer and closer and closer and closer until we finally find a point that is, that marks the average rate of change. So it's not perfect, but it's a interval around the point that we're looking for. So that's why it's an average. This method is called finding the secant line. While it is easier to a degree than finding the tangent line, we're on to bigger and better things in grade 12 where we're finding the tangent to the curve. So a tangent line is a line that touches a curve at a function at exactly one point, like I talked about right here. The equation of the tangent line represents the instantaneous rate of change at that exact point. The main two ways of finding the equation of the tangent line for a given function is to either use first derivatives, yes, or first principles. First principles is something that we learn in calculus. Honestly, I'm not a big fan of it. It's a lot of steps, a lot of limits, a lot of things that you don't need to worry about when using derivatives. As you see here, I'll be covering derivatives. So let's go through two quick examples. Let's see the question here. We got f of x is equal to 3x squared subtract 6x plus 4 at x is equal to 4. So basically what this is asking us is 3x squared. So let me take a peek right here. I have 3x squared right here. And as you guys can see, it's kind of a concave upwards graph, and we're finding the instantaneous rate of change or the tangent to the curve at x is equal to 4. So as you can see, x is 4 right here, and we want to find the point at this point. So you can kind of cheat and see that the first step is finding the point at 4, so the corresponding y-coordinate. We can kind of cheat on Desmos and see that, if we type in just x is equal to 4, we know that it's equal to 28y. But again, we can find this out algebraically as I did right here. So going into highlighter, we have the first step you're always going to want to do is put whatever you're finding, so 4 in this case, you're going to want to put that into your function and see what it spits out. In our case, it spat out 28. So we know that the points of tangency, so the point that we want the tangent to touch at only one point is going to be 428. Cool. So next step, we have the slope. And the slope of the tangent is going to be finding the derivative of the tangent and inputting the value of x. So the derivative of this equation right here, again, this is simple power rule. Take the 2, bring it to the front. 2 times 3 is 6. And 2 subtract 1 is 1. So 6x to the 1, imaginary 1 right there. And then right here, there's imaginary 1. 1 times negative 6 is negative 6. 1 subtract 1 is 0. X gets canceled out. And then you're gonna want to input your 4 in here, see what this spits out, and we get 18. So we now know that the slope of the tangent is 18x, so pretty steep slope. It looks something like that, more or less, more straight than what that is. But we have the slope of the tangent 18x here. Finally, our last step is we have, I'm sure all of you guys remember from grade 9 that this is the basic equation for a function, and it is y is equal to mx plus b. We have, and if we go through each component, y, we have a y coordinate right here, x, we have an x coordinate right here, m, we have a value for m, all we're missing is b. So what we do is we plug in those values and we solve for b. So 18 times 4, and then 28, and then you do a little bit of algebra here. Again, this is like grade 9 level algebra. And you're going to end up with b is equal to negative 44. So as you can see, we have all the values that we need in order to plot this function. And the final answer, of course, is y is equal to 18x subtract 44. So I like seeing a visual when I come across these kind of questions. So I went ahead and graphed this on Desmos. And as you can see, we have the graph of the original graph, and then we have the graph of the tangent line, the equation of the tangent line. So for some reason, it doesn't show that it's at 28, but if we go x is equal to 4, right here, we see that the green and the yellow curves, they intersect at 428. So we know for a fact that the tangent to the curve at 428 is equal to this, 18x subtract 44. And we're on to our next question. Next question is more of the same stuff. We have h of x. Let's change the highlight color to orange. We have h of x is equal to x squared subtract 4x, all put up to the second exponent, subtract 9, and we're finding the value of the tangent, the point of tangency, the x value of tangency is 5. So again, let's go through the steps. We got to find the points. So the points is finding the x and the y. We already have the x, so plug in the x into the equation. You can see right here. And it's going to spit out 516. We can confirm this by looking at the graph of the function and hitting x is equal to 5. And boom, right there. X is equal to 5, 516. We are correct. So moving on to the next step. We have the slope of the function. So finding the slope of the function, this can be a little bit more challenging because it involves the power of a function rule. But don't fret, we've gone through this. So we have the original function, and we're taking the derivative of the original. So once again, you're going to want to bring the 2 down in front of the brackets, as I did right here. Subtract 1, 2 subtract 1 is just 1. And then don't forget, this is a crucial part that I've forgotten many times. You're going to want to take the derivative of whatever's inside, whatever that is, and multiply it at the end. So we got the derivative of x squared is just 2x, and then the derivative of negative 4x is just negative 4. Now we have this simple equation right here. Multiply the first and last terms like I've talked about. We get 4x subtract x, so that's that times that times that. And times the original, plug in 5, which is the target value that we're looking for, as you can see right here, and we get a slope of 60. So again, very steep. This is even steeper than the last question. This is getting closer and closer to a vertical line. Again, that is not very good, but yeah, you get the gist of it. It's just supposed to be a near vertical line. Okay, last step here. We're going to solve for the equation. Again, we have the y, we have the x, and we have the m. All we have to find is the b, which is the y-intercept. So you plug in all the values that we know to solve for the values that we don't know. And it turns out that b is equal to negative 284. And that means that the equation of the line of tangent, the tangent line, is equal to 60x subtract 284. We can verify that by showing that. And again, it doesn't show for whatever reason, but if we do x is equal to 5, we can see that these two functions, the red and the green again, they intersect at exactly 516. And yeah, we know that we're done. So I hope this helped out a bit. I only included two examples for this because it was a pretty simple topic that we've sort of glossed over in the previous grades. But yeah, thanks for watching, and hope to see you for part 3.